All right. Welcome to, I guess, the fourth lecture on this. And this one is all about fossil fuels. And so looking at how we use fossil fuels and looking at predictions for the future on fossil fuels. Of course, this is all linked to climate change, so there'll be kind of like a underlying part to that. So here we go. So this diagram here looks pretty complicated, but it's just where our energy comes from and where does it ultimately end up, right? So um, over on the left here, you can see hydro, biomass, geothermal, wind, solar, nuclear, coal, natural gas, and petroleum. Those are all things that we've talked about before in the way that we generate electricity. You can see that for the most part, right, these top mm, top ones here, those are all largely, especially coal, being used for electricity generation. Um, so a little tiny bit of petroleum. You can see that natural gas is, somewhat being used for residential. So that'd be running your furnace in your house and cooktop or hot water or whatever. Commercial as well. So, factories and whatnot. Um, you can see that I guess industrial would be factories and whatnot. Commercial would be, um, businesses and things. Petroleum, you can see that petroleum is largely what's being used in our transportation, which would be down here. Um, and then ultimately things end up as useful energy. So like we've been talking about the 30 that things are generally 33% efficient. And so, sure enough, you can see that in all of these, you have these little red arrows going off that are showing the energy that ends up being useful versus, right, like all the energy that is wasted. So that'd be like the waste heat of driving your car. Same thing with the electricity, right? Again, the electricity is being distributed to these areas, but then um, there's a lot of waste heat as a result, or energy as a result of generate electricity, heat that has to be released in the environment. That was in right our last lecture. We talked about that. Taking a look at the next one. So, what are fossil fuels, right? So, before we get into that too, or before we get too far down here, so fossil fuels are biomatter that was trapped in rock formations from millions of years ago, right? I said powered by dinosaurs at the beginning of the thing, but of course it's powered by anything that was alive millions of years ago. It's usually usually plants and things like that that have been now crushed and buried and underneath there, and so they have slowly turned into fossil fuels. They're technically what's called hydrocarbons. Hydrocarbons would be made of hydro, like hydrogen, and carbons. It's hydrocarbon. And we usually think of fossil fuels that we use the most are things like coal, oil, gasoline, natural gas. Those would be examples of that. Where does it come from? So, right, in order to get it, it's underground usually. So like for example, coal, we have to mine that. So, looking at this picture down here in the bottom left, right, we have these huge mines where you dig down, you get it, you sort it, you go manufacture it to get it to a useful thing. Um, oil, oil we get from deep underground. So we have, in the oceans, we have big oil well drilling rings on the surface. We drill these big, deep, these big oil wells down to get to it, pump it out. Then it, of course, has to be refined and things like that. There's also tar sands. So I think primarily in Canada, there's something called tar sands, which I guess I don't know that much about it. I would assume that it is sand and tar mixed together, in which they can extract the oil from that. I think that's a uh, much more inefficient process than pumping it out, drilling down. But still, it's a way that we can get it. Becomes especially more important when you start to think about where oil comes from. So, um, we of course have some areas in the U.S. where we can drill for oil. Alaska, Gulf of Mexico being some, but of course, um, right, we get the U.S. gets a lot of its oil from the Middle East, and so you know is always kind of, I guess, beneficial to think about where we can get oil that is local. One, because you don't have to transport it across the ocean, but then two, um, right, economically, it's much more stable to be getting oil from um, right from our own country versus maybe a country that is at some to a certain extent in some unrest. Right, so it's not like you just pump it out of the ground and put it in your car. Of course, you have to refine it in some way. So we start out with what's called crude oil, just exactly like it sounds, crude oil, so unrefined. You then have to transport it through pipelines or oil tankers to refineries. So from wherever you get it, you have to get it to a refinery, right? Um, it's refined at a refinery. This is also an energy, right? A process that takes a lot of energy. So that means, right, you have to take it from the crude oil, which can't really be used for a lot of things, and turn it into gasoline, diesel, um, you know, or whatever oil that you want to use it. So you have to, right, change it into what you need. Right, once you have it in the form of your gasoline and your diesel or whatever, your oil, burning oil, you then have to transport it to the store, the home, or the business, or whatever that you're going to use it. So you have to get the gasoline from the refinery, so put it in a truck and truck it over to the gas station. Or your house is heated with oil, you have to transport that heating oil right to your house. You have um, natural gas has to be piped to your house, so or propane has to be delivered in a truck. So all of these process, the drilling, the transporting, the refining, transporting again, all of these processes take energy to make that happen. So so how does a fossil fuel work, right? Right, as I said before, it's a hydrocarbon. And so that means that it is made of mostly hydrogen and carbon. So hydrogen can be combined with oxygen to get H2O, which you know as water vapor, right? So basically, that part is not as terrible for the environment. Water vapor is a greenhouse gas, but it's not nearly as bad as CO2. It's easier to remove from the atmosphere than CO2. And so, uh, yes, it is problematic, but not terribly problematic, or not as much at least. We have CO2, carbon, right? So you have carbon molecules or carbon atoms in your fossil fuels. When you burn them, they are combined with oxygen to form CO2, carbon dioxide. So if we look at like the basic three for fossil fuels, right? Coal is mostly carbon. So when you burn that, it creates mostly CO2. That's one of the reasons that coal has gotten such a bad rap. It is really terrible for the environment because it emits so much CO2. Oil has about twice as many hydrogen atoms as carbon atoms. So it does emit, like when you burn the gasoline in your car, it emits more H2O than CO2. By the way, anytime you make these combinations, so anytime you're combining your hydrogen with your oxygen, or you're combining your carbon with your oxygen, you're releasing energy. It's going from a higher energy state to a lower energy state, so it's releasing energy. Um, so with oil, it produces more H2O than CO2 for a given energy output. So better than coal in that sense. And then natural gas is actually the best out of all of them. It's made of mostly methane, which has a lot of hydrogen, right? Note the H4 in there. And so as a result, right, four times as many hydrogen atoms as carbon atoms. And so it's going to create even more H2O than CO2. So it's out of all of them, the cleanest burning one in that sense, right? Produces the more water vapor than CO2. Um, so Um, so how we use fossil fuels. So, right, we use them for lots of different things. We've already talked about how we use them to generate electricity. Um, we also use them for transportation, our trucks and our cars and our trains and our planes and our boats and whatnot. We use them to make plastics. We use them to make oil and lubricants and also to make fertilizers. So we use them a lot for a lot of things other than just electricity generation and transportation, which are the ones that you um, think about the most. And so, one of the things that makes, as we think about like trying to wean ourselves off of it, it's problematic because, um, like, sure, can we decrease our use of fossil fuels for power generation and transportation? Like we're already starting to think about how to do that, but of course, plastics. Like, think about how much plastic we use, and right, that we're gonna probably still need to continue doing that at least for a while. Same with fertilizer. So, um, it's one of those things that the problem is it's kind of more widespread, but obviously the power generation, transportation are huge. Um, so if we can decrease that, that'll be pretty helpful. Um, so just to kind of remind you about how fossil fuel plants work, or just any steam engine here. Um, so would be what's called an external um, combustion, right? So as opposed to like an internal combustion engine, like the engine in your car, that's an internal combustion engine. So let's just kind of trace this out, right? So we're going to start here um, with with our boiler. Okay, so we're going to put fuel in here. Let's get red better. We're going to put our fuel in and our air in. So that's going to be right our hydrocarbon. So our hydrogen or our carbon, and right we're going to put our oxygen in over there. We're going to burn them. Um, and of course, right, you get your pollution coming out there. That's going to create heat, right? The main product off of that is going to be heat. And so we're going to have water coming in. We're going to heat that water. So now you got water leaving, and that's hot water, right? So that water is basically turning into steam. The steam is expanding, so it's increasing the pressure, and we send it through a turbine, basically. So basically, in order for the steam to escape, um, we need to, right, we're going to make it spin this generator on its way out. You then need to, right, cool that water back off. So we put it in what's called a condenser here. And so basically the condenser is surrounded by cold water. So, water from the river, lake, or ocean or something like that, water that's cold. And so, right, that's going to cool the water back off as it goes back um, into your boiler. Um, right, so now you got this kind of warm water that's come from the lake, river, lake, or ocean. You got to cool that off. So you got this hot water, and we're now going to send into what's called a cooling tower. And basically, what this is just emitting most of the heat into the atmosphere. Um, and so, right, because what we don't want to do is pump that water right back into the ocean. Because if you're pumping, or river or lake, if you're pumping that much heat into the river, lake, or ocean, that's going to be hard on the fish and the whatever lives in that ocean or it lives in the river because you're basically pumping a lot of heat right into that, and so that's not good. So you want to right send that off into the atmosphere first before sending it back. So that's basically the idea of how a steam engine is going to work. So and how we're burning fossil fuels. This could be we could use the same idea for nuclear nuclear fuel, just you're instead of burning fossil fuels, you're heating it with nuclear. But that's the basic idea there. Oops, sorry. We use it for transportation. Um, right, you're burning your fuel, your gasoline coming in or your diesel. Um, right, the engine is going to be to a certain extent. It's going to send about 62% of its energy is going to be from heat. So that'd be heat coming off of your engine. Another 20% ish is the friction of turning the motor. Right, motors do not turn very easily, even though there's lots of lubrication and stuff in there. Um, so, so you get your mechanical energy that's now leaving. You got maybe 20%, and of course, some of that's being used to run your accessories. So maybe the alternator, which is creating electricity, which is powering your seat heater and your radios and your whatever that's running in your car that's using electricity, sat nav, and all that stuff, right? Fans, blow, climate control or air conditioning or that kind of stuff. Your transmission and drivetrain, of course, is going to be reducing it even more further because you're going to lose some energy, to the transmission. Um, so you're now getting only about 15% of the energy that you actually started with. Um, out of the, all the energy that you burned, only 15% is actually making it to the kinetic energy of the car. You're of course going to lose some of that kinetic energy to air resistance as the car goes through the um, through the air. And this is of course going to become greater the faster you go. So if you're driving around at 80 miles an hour, you could expect this 5% to increase. Rolling resistance, right? So it takes energy to move your tires along, and so you're losing air, energy to that. And obviously whatever's left is going to be moving your car until you hit the brakes, in which case the rest of that energy goes off into the brakes. So this is where, the kinetic energy of the car is going to be ultimately taken by one of those three things. You know, air resistance as you drive, tire losses as you drive, brakes when you stop. So, all right, so there you go. The big question, of course, is will we run out? Okay, and so this is a we're concerned about fossil fuels for for climate reasons, and then also it is a finite resource. There's only so much on Earth, and so you're going to end up. Right, are we going to run out? The answer is it's kind of right. It's kind of complicated. So we're going to now dive into why is it so complicated. Um, let's think about like just trying to approach this problem from a general standpoint, the basic approach, right? Like you're going to actually do this in your homework. I have a problem where you're going to do this basic approach. You're going to estimate how much oil is left. So the different oil companies do this. They estimate how much oil is left in the reserves. And then you divide by the rate at which we use energy or how much we're using. So, there are 5 gallons left and you're using 1 gallon per day. Right, you'd run out of gas in 5 days. Okay, that's obviously not real numbers. Um, Now, of course, when we do this approach, there's some issues, right? When we estimate how much oil is left, that's not going to take into account any oil we haven't found yet, right? So they're always doing exploring to, test wells and whatnot to try to find more oil. And so our estimate is going to probably be an underestimate of how much energy is actually left. It also doesn't take into account any changes in the rate of consumption. So maybe we use more energy, or maybe we use less energy. Right, the very basic approach isn't going to take that into account. So is the consumption going to go up or go down? That's actually kind of complicated to say, right? Now, when you think about it, like and what has happened up until now, is that right the population is increasing. That's more people driving their cars. That's more people consuming products. That's more houses being heated, and so consumption would go up. The other side of it is that consumption could go down as the prices climb, right? So if you know very much about supply and demand, right, as the supply of the product becomes limited, the price is going to go up, and so as a result, right, you might people might start using less um, because people might start using less um, because it's more expensive, right? If it costs you $100 to fill up your car, you might drive it less because it's so expensive. And so, um, anyway, those are a couple of things that are the basic approach. So you're going to do the basic approach in your homework, but of course, keeping in mind that it's not taking into account these things. So let's see here. So how do we kind of, so obviously people have studied this and take this into account. In this sense, something called Hubert's curve. And basically it says that, right, like over time, and this would be like a long time frame because we're talking about our overall, over the time fossil fuel usage, so hundreds of years ish, right, that we're going to use more and more oil production rate, more and more oil, and and then you reach a certain point and it's going to decrease, right, and then we'll start to decrease our oil usage, and that the area underneath the graph is going to be equal to the amount of oil reserve we have, right, oil reserves, um, and that is a pretty set amount, right? You only have so much oil available to you, um, and so the area underneath this graph would be equal to that, okay? And Hubert's curve says that, right, if this is going to go smoothly, the peak is going to be somewhere around um, when when we've gone through half our oil reserves. That we gotta right then we gotta start decreasing our oil production. Um, in that case, it would go somewhat smoothly. But not everyone necessarily agrees with this model here necessarily. And so, right, let's take a look at the data so far. So we really started ramping up our oil production um, in about the 1950s. Oops, shoot. In about the 1950s is when it became, a lot. And so as we trace this, the green part is the historical part. So, you can see it kind of switch to um, blue somewhere in, 2000, 15. This graph's a little bit old here. Um, and so we can see this, right, continue on up here. And so the question is, what's going to happen? They note the 2016 date. But, right, what's going to happen is, are we going to continue to use oil and continue to go up? Or, right, is it going to start to drop off as though, like, the Hubert's curve is saying you should do, right? Now, the pain is going to be much more painful to continue going up because this huge decrease is going to be expensive because it basically means we are not prepared um, versus this kind of more slow to decline, right? Things can adapt more slowly. If suddenly we're running out here in 2037 and everybody's driving around gasoline cars and suddenly there just isn't gasoline because it's so expensive, right, everyone's gonna have to buy new cars and that's gonna be kind of rough, versus right declining at a more gradual rate. And so, right, the first model or the model where we decrease, here at 2016, um, that would be much more like the Hubert's curve one versus this is kind of we continue to ignore the fact that we're running out of oil. We don't change anything. We don't change course. Right at some point, the estimate says 2037, we're going to suddenly have this sharp decrease because right we only have so much oil. The area underneath the graph needs to stay the same because you only have so much oil. And so, right, you can't like trail this off out like this because that adds way too much area to the graph and there just isn't that much oil. So it's going to have to be a sharper. So the more we continue on up, right, the sharper the decrease is going to be and therefore the more expensive and the more painful um, right, it's going to be when we finally run out. So we just continue ignoring the problem, and you're going to end up with this sharper decrease. So the question is, where are we? Right, this graph is older. Have we started to see a decrease in our production rate? So here's a graph from I believe 2019. Oh, let's get rid of all this. And what you can see is, so oil is going to be the one in green here, and that we have not turned around, right? As we look at our oil consumption, we're seeing a pretty steady trend here, and no signs of decreasing our production. So um, so right, we are continuing on up with our production. So, other factors that affect how long we can continue, or like until we run out of oil, right? So, other factors. So far, we've talked about the amount of supply left, right? So we just said we're just only so much left, and the rate at which we use it. So that's right. Remember that my answer to the question was, when will we run out, or will we run out? Kind of. So some things that affect when we will run out, or when we will have to change, is the price, right? So keep in mind that right as we start to run out of fuel, the price is going to go up simply because right that's how supply and demand works. Supply goes down, demand goes up. Um, or sorry, so supply goes up, supplies goes down, the amount of um, the price goes up. So therefore, if the price goes up, consumption will decrease, right? If it gasoline reaches $5 or $6 a gallon, you're just not going to want to drive as much, right? Um, so obviously, that's part of that. We also, right as price goes up, we're going to be more encouraged to come up with alternatives. So we can figure out alternatives to fossil fuel consumption. So perhaps figuring, figuring out cleaner or cheaper ways of doing things. Could be electric cars, could be hydrogen fuel cell. Like who knows? Um, Hydrogen fuel cells. Like there's different ideas out there that people are working on to try to figure that out. It's of course very complicated, but those are some things. An example of this of the alternative thing would be that like we have a lot of coal left. Like we are not running out of coal in the United States. That's not a problem, right? But of course, we are seeing a decrease in our electrical power generation because right of using coal because of natural gas. You've maybe heard of fracking. So they do fracking in order to find natural gas. And so basically, what happened is that we have a ton of natural gas, and so it's cleaner and it's cheaper. And so basically, we're decreasing the amount of coal that we're using. One, because it's bad for the environment, but two, we just have found a better way of doing it, an alternative way of doing that. And so even though we're not running out of coal, we're using more and more natural gas. Still problematic, still a fossil fuel, but at least it's better than coal. And so, this would be an example where the alternative is affecting how, right, when we, are stopping using coal. The other thing is, right, things can be controlled through taxes. So we can control carbon emission by basically artificially increasing the price of the product. Therefore, kind of artificially increasing the, well, like basically doing what we were talking about with price, where as it becomes more and more expensive, consumption will decrease. So you just make it more expensive by applying a tax to it, and then therefore it consumption would in theory decrease. So the problem is, and that would also increase the incentive to come up with alternatives. So quick talk about taxes here, or just government regulation. I suppose maybe that's what I should have titled this, right? So the current problem is that our economic system, especially in the United States, doesn't apply a cost to the environmental impact of fossil fuels. Meaning that if let's say you burn fuel, right, that is free. Like you pay for the fuel, but like it doesn't cost you anything. Maybe you like you know, let's maybe put this instead of a fossil fuel, let's take this in terms of like, let's say you cut down a tree in your yard, and you burn it. Okay. Um, in theory, that costs you $0 in order to do that, right? Um, the tree was yours, and if you were able to cut it down yourself, then it doesn't cost you anything to cut that tree down. However, the cost to the environment is not zero, right? You've put a bunch of carbon into the air, and so right, our economic system doesn't take that into account that there is a cost to putting carbon in the air, right? Because you burning your tree adds more carbon to the atmosphere, which then increases the um, greenhouse gases, which increases the temperature of the earth, which of course is going to cause problems. At some point, that's going to catch up with us. There's going to be costs associated with that, and so there's a couple ways to think about this, or that the government thinks about this, or that economists think about this, right? One is we can do a carbon tax, which is what I was kind of talking about before, right? You basically apply a tax to the fuel um, on the amount of carbon emitted by that. So, like, probably coal would have a fairly large tax, natural gas might have a smaller tax. And this is going to cause, oops, sorry, this is going to cause a decrease in consumption, right? Um, So that right, and therefore decreasing carbon taxes. Um, there's also something called a cap and trade system, which is what Europe uses. And it's basically right, the government is going to set limits on the amount of carbon emissions that a certain industry could produce or a certain company could produce. If they come in below that, they could sell those or those carbon caps, or points or whatever to a different company. So that would kind of incentivize them to come up with cleaner and better ways to do it because they would basically be allowed to, um, make money off of the fact that they're not polluting. So it's just a way of incentivizing companies to use less carbon because they can make money by not producing carbon. Um, so, it is actually fairly accepted that one of these options is the best solution to climate change. There are various solutions to climate change, and it's going to be probably a combination of these of different solutions. So there's also things like something called geoengineering. I believe it's called geoengineering, where you could affect the climate by putting something into the atmosphere. Um, that's fairly risky and sketchy. Um, so that's one of them. I don't recall. There's a third one, and I don't recall that. But basically, we need to start using less fossil fuels, and these are the ways to do that. So you just, in order to change the way that we use um, energy, the government has to step in and make decisions, and basically start applying a amount of a cost to polluting, more or less. Um, and in fact, this guy called William uh, Nordhaus, who's an economist, actually won the Nobel Peace Prize for his work on this topic in, I believe, 2018, like quite recently. And basically, he was saying, um, this is what we need to do. Like, this is how we fix climate change. Like, it is possible. We do it this way. And the plus side of it is it is a it's a solution. It's a doable solution. It's possible. But the thing is we need to start now. The government has to start taking responsibility to this because, again, right, going back to that graph, the longer we wait, the worse it's going to be. The harder that's going to get to get off of fossil fuels. So there you go. Well, that's the end of that. As usual, right, good luck on your homework. Let me know if you have any questions. Email me if you got questions. And thank you very much. Okay, bye.